This question belongs to compiler design subject and was asked in GATE 1991. So the question states, consider the following grammar for arithmetic expression using binary operators minus and divide which are not associative. E implies E minus t slash t, t implies t divided by f slash f, f implies e slash id, where e is the start symbol. And it has two parts. Let us see each part one by one. Part A states, is the grammar unambiguous? If so, what is relative precedence between minus and divide? If not, given unambiguous grammar that gives divide precedence over minus. First, let me tell you what is the meaning of this non-associative. Non-associative, if minus is non-associative, it means A minus B minus C is not equal to A minus B minus C. And divide is not associative, which means A divided by B divided C is not equal to A divided B whole divided C. Which means we can't change the associativity of this parenthesis. Now, when can we say a grammar is ambiguous? A grammar can be said to ambiguous if any derivation of a string has more than one either parse tree, more than one parse tree, or more than one leftmost derivation tree, leftmost derivation, or more than one rightmost derivation. In leftmost derivation, we are always expanding the leftmost non-terminal, and here we are always expanding the rightmost non-terminal. So the grammar is ambiguous, but finding an ambiguity of a grammar is an NP hard problem. So how can we prove that a grammar is ambiguous? So we basically try to find out a string for which we can generate more than one parse tree, LMD or RMD. And if we are able to find a string, we directly say the grammar is ambiguous. And if by hit and try methods we are not able to find any string, then we can conclude that the grammar is unambiguous. Let me try to generate more than one parse tree if I can. Let us take strings like id minus id divides id. Let us try to generate the parse tree for this. So we have e implies e minus t. Okay. Then we have t implies t divides f. Then we have t implies f, f implies id, f implies id. So this part is done. No, here we are generating a wrong thing. So let me try to redo it. Sorry. So here what we will do, first we will try to bring this divide symbol. So what we will do, we will start with e implies t, t implies t divides f. So here we have brought this divide symbol. Now we will do f implies id. So this part is done. Now what we will do, we will do t implies f, f implies parenthesis open closed as well as e. Then we will do e implies e minus t. Then we will do e implies t, t implies f, and f implies id. And then we will t implies f and f implies id. So we have done it. id, so we have generated id minus id divides id. But we are only able to generate one string, one parse tree for it. You can try to do some try runs. You will get to know that for each string you can generate only one parse tree is possible. Thus the grammar is unambiguous. So you need to do it by hit and trial method, whether you are able to find a grammar or not. So in this case, we come to the conclusion that the grammar is unambiguous. Now, what's the further part of the question? It says, is the grammar unambiguous? Yes. If so, what is the relative precedence between minus and divide? If not, give unambiguous grammar. So this part has no significance as it is already unambiguous. Now we need to give the relative precedence between minus and divide. Okay. So higher precedence has more depth. What is the meaning of higher precedence? Higher precedence means it should be evaluated first, and we can evaluate the expression first if it has more depth. See, draw the tree for this grammar. E implies e minus t. Then we have t implies t divide f. Here you can see. here divide has more precedence than minus. Thus divide has more precedence than minus. So the answer is divide has more precedence than minus. Now let us see the second part of the question. So part B states, does the grammar allow expression with redundant parenthesis as id divides id? This is redundant, as even if this parenthesis was not there, id divides by id will have the same output. And even if this parenthesis is not there, id minus id divided by id will have same output. As we have already seen that divide has more precedence, so divide will be evaluated first and then minus. So we have to see whether this allows these expressions or not. Let us see whether it allows id divides id or not. So what we will do, we will try to generate the tree. So we will do E implies T implies F implies open parenthesis, E and closed parenthesis. Then we will do E implies T implies T divide F. Then we will do T implies F implies ID. Sorry. And here we will do F implies ID. So here we have generated ID divides ID with an open and closed parenthesis. We have easily generated. So this can generate this. Now let us see whether it can generate the second one, ID minus ID divides ID. So for this, let me try to draw the parse tree. So the parse tree for this will be something like this. E implies, we will have E minus T. Then we can do E implies T implies F. We can do F implies ID. For this T, we can do T implies F implies open and closed parenthesis E. Then we can do E implies T implies T divide F. Then T implies F implies ID, F implies ID. Now let us see whether we have generated it or not. We have ID minus open parenthesis, ID divides ID closed parenthesis. Yes, we have generated this. So this means yes, we can generate redundant parenthesis, as this parenthesis is redundant. Why is it redundant? Because even if we have ID minus ID divides by ID, even then as divide has more precedence, so it will be evaluated first only. So there is basically inherent parenthesis is available due to this higher precedence of divide. So there is no need of writing these parentheses. So now what we need to do? Yes, it allows this. If so, convert the grammar into one which does not generate an expression with redundant parentheses. Okay, and we have to do this in minimum number of changes to the given production rules and adding at most one more production rule. Okay, so we are given this grammar. So now what they are asking us is that we should convert this to a grammar which does not generate the redundant parentheses. And for this we can add at most one extra production rule. So how can we do this? Let us suppose we will take it same like this, E implies E minus T. With E dash we will also try to generate E minus T, but not T. T can't be generated with this. Now we will have T implies T dash divides F and ID, the same over here. And then T dash can also derive T dash divides F. These are pipelines operator. This is pipeline. T divide F and F. And then we can have F implies E dash pipeline operator ID. Now let us try to generate the strings, whether we can have redundant parentheses or not. So ID divides ID is a redundant parenthesis. Let us try to generate it with this. So how will we do? We will start with E. Okay. Then we have to bring this parenthesis. So we will go to E to T, then T to, we can't generate if we come from E to T, and then T to, we can't generate parentheses over here because parentheses can be generated only by E dash. So thus we can't generate this. Thus this is our answer, and this grammar is not able to generate the redundant parentheses. So this is the answer for part B, and we can generate redundant parentheses.